Hey, welcome back to Fat Mama Physics. In this video, we're going to talk about half-life and the calculations that go along with half-life. So I'm going to be mostly doing examples, but maybe what I'll do in this first video is I'm going to do a quick coverage of half-life and maybe just filling out a table together with us to kind of give us an idea about half-life. Half-life is in fact a little bit the name itself is not quite intuitive as it sounds. So let's give us a better idea of what it is. So the idea of half-life is it's a measurement of time. It's the time that it takes half of a radioactive sample to decay. Or either way, the other way of phrasing it is the time that it takes the activity of the radioactive sample to half. So either we're talking about the definition in terms of radioactive nuclei, or we're talking about the activity of a sample. The activity represents the rate of which a sample is decaying. The units of it are in becquerel. So that's essentially how many decays are you getting per unit time, per unit of seconds, okay? So the half-life is measuring the time for, if this is my sample, half of them, the time for half of them to fully decay into the daughter nucleus. You'll have half the sample left, which is still radioactive. If you're talking about activity, then essentially is the time that it takes the rate of decay to slow down to half the rate of which it was decaying to begin with, okay? So let's look at an example here of a table. So here we have a table of radioactive decay of thallium-208, and if we take a look at this chart, it looks like the half-life is, what is it? What do you think? And if you're saying 3 minutes, yes. It takes 3 minutes for one half-life. So then we can just completely fill out this table here. Okay, so in increments of 3 minutes. So then let's take, that's a really fast half-life. So very highly radioactive. So, okay, so let's take a look at what this means. When thallium-208 is fully intact, so before we start counting the time, we have all of the nuclei in the parent form, which is thallium-208. So the fraction of the parent nuclei is 1, or in percent is 100%. The fraction of the daughter nuclei means whatever thallium decays into. It doesn't tell us in this question what it decays into, but it decays into something. And whatever that something is the daughter nuclei. At this point, there is none of it right now because we haven't actually started decaying yet. Percent is just going to be 0. And I'm just going to put brackets percent here so I don't have to keep writing percent. That's going to be the unit of that particular column. So after 3 minutes, what happens is that half of the parent nuclei will have decayed into daughter. So the fraction of the parent remaining is going to be 0.5, which is 50%. Oh, I just wrote percent again. And where's that 50 going? 50% is decayed into the daughter nuclei. So this is going to be 0.5 of a fraction, which is 50%. So in a whole, after 3 minutes, if I have a whole sample, half of it is going to be parent, half of it, which is thallium-208, half of it is going to be daughter, whatever thallium decays into, okay? So after 6 minutes, what's going to happen is that half of the parent will decay again. So it's not half of the full, it's half of the half. Okay, so what that means is half of 0.5 is going to be 25 parent of 25% of the 50% will decay. So percent parent nuclei that's going to be left is going to be 25%. Now, the daughter nuclei, we still have a 50%, but 25% more becomes daughter, we're going to get a whacking total of 0.75. Okay, and then as a result, 0.75 is going to be 75% in the percent form. I just kept writing percent anyway, so let's just get rid of that. Notice something. Notice that the 0.25 plus 0.75, it gives us exactly 1 if you add the two together. So that is correct. Every time when you're doing your calculations, the amount of parent plus a daughter added together should always give you 100%. Okay? So after another 3 minutes, then we're going to lose another half of the 25% of the parent. So in this case, this is going to be 0.125, which is 12.5%. We've lost again to the daughter, and which this is going to be, if I can do my math properly, this is going to be 0.875. So 87.5% daughter. Okay, so notice that the first half-life, there's a stark increase in the amount of daughter. Then it starts to slow down. Very interesting. So it actually represents very well how radioactive decay works. So at the very beginning, you have a really high radioactivity, and then over even a long period of time, sure, your activity drops very down to very low, but you're still going to get a bit. You're going to get a bit and get a bit, okay? Which is why storage of fission materials for nuclear reactors is very annoying. It's going to take a very long time for them to have close to zero radioactivity. Okay, sorry. Backstory. Okay, so let's keep doing this. 0.125, half of that is going to be 0.0625, in which this is going to be 6.25 parent remaining, and then we add that to the daughter, which is going to give us 0.9275. And that's going to be 92.75 in percent form, okay? And again, half of this is going to be 0.03125, okay? And percent left, 3.125%. And fraction of daughter nuclei, which is going to be, adding that again, 0. This is going to be 6. This is going to be 8.75. So a whacking total of 96.875%. Okay, so there you go. So anytime when you add up these two numbers together, always gives you 100%. Okay, so this is kind of the essence of how half-life works. So in the next video, I'm going to do an example on half-life, using activity, using the concept of half-life. We won't delve into the equation. That one is for HL physics. Otherwise, you can watch some of those later on as well. Thank you for watching, and good luck, fam. I'm Physics, signing out.